Well, thank you. Good morning, and thank you, Mia and Statera, for inviting us for presenting here today. It's a pleasure. I'll be presenting two case studies from projects we have implemented here at Remediation today, both involving high viscosity and heavy end hydrocarbons. So basically, very similar products that we may encounter across your sites. Before I move into the case studies, I'll just go through a quick presentation about Remediation. I have one slide on principles that I think are important to consider before implementing remediation. A lot has been covered by John on his presentation, but I'm just going to touch on those a few specific points there, and then I move on into the main case studies I'm willing to share with you today. Just waiting for the slides.
Sorry, we're just having some technical issue. Give me some time to share the presentation.
No problem. As an introduction for Remediation, so we save some time here, we have 24 years of experience. Remediation was established in the UK and since been running projects across Europe, Middle East, Africa, Asia, and Asia as well. We are a remediation specialist contractor, so we experience in a range of technologies, ex situ, in situ technologies, and what we do, we tend to do what we call a scientific-led design for remediation. So what that means is that we understand the problem, we dive deep into understanding the requirements of every single site we're dealing, the problem, the type of contaminants, and then we assess and identify the best remedial solution for that specific site or condition. And that's the main ethos within Remediation and how we try to develop and implement solutions to our sites. As a brief introduction to the first case study I'll be talking today, before I can talk about the principles, that's a site, basically the sites we had in Widnes in the northeast of the UK, and where there's a legacy high viscosity oil in the subsurface, really high viscosity, really difficult to recover under normal conditions. So the challenge on that site really was, here we go, I got my, so if you could please skip to next, if you could skip next, please. Next. If you go into the principles of next one, please. Here we go. So that's basically a catch up with John's presentation, as I mentioned. The key points on when you're procuring, designing, implementing remediation that I believe you have to consider is one, is having a very robust conceptual site model. And that's exactly what was well described on the different slides from John. You need a very good site investigation. You have to understand your soil, your groundwater, your contaminants, the environmental factors affecting your site, and the site constraints that will be affecting the remediation. With that in mind, and with that knowledge, you can then build a very robust conceptual model, and that conceptual model will inform on the best solution for your site. And that links me to this next bullet point, which is there's no one fits all solution. Every site is different. Every contaminant behaves differently under different settings. So a careful assessment of the remedial options, the technical viability, the commercial viability, the likelihood of achieving the objectives is really important when you're designing, procuring, implementing remediation. And a critical part of this process often involves laboratory field trials to assess the viability of different technologies. And this is important because it provides a critical information for the design when it comes to not only the technical aspects in terms of treatability, but also likely timescales and costs. So that helps really reducing risks associated with your remediation scheme or the remediation program. Next slide, please. So moving to the first case study, next please. So as I mentioned, that's an industrial facility with a legacy contamination. So basically on the photo on the left of your screen, the contamination, the high viscosity oil was present beneath that subsurface on that slab, and was there for many, many years. Over the years, there were attempts to remove the oil using skimmers under ambient temperature. That was very ineffective, with 6,000 liters removed over the course of 6 years. We were then invited to revisit the site to look at options to enhance the remediation and move into completion or closure of the site. So we identify steam enhanced extraction as a potentially viable technology. The principles being that the steam would add temperature to the ground, heat the oil, reduce viscosity, increase recoverability, and then with that, we then maximize removal. And so before we move into the full scale implementation, we went through a process of detailed designing and trialing, which is on the next slide, please. And the design stage really focus on two main aspects. Point number one, which is the picture on the top of your screen, was understanding the behavior of the oil under different temperatures. What that means that by increasing temperature, we're reducing viscosity. By reducing viscosity, we made the oil more mobile and removable. And what we wanted here was to identify the lowest temperature that we could achieve to make the oil recoverable. And that is really important when it comes to the life cycle of a project, because you talk about energy to achieve temperatures. So if you understand the minimum temperature you have to achieve, you'll be spending less money with energy, and you make it more cost efficient and sustainable. The other important points for when assessing thermal enhanced technologies is really understanding the ability to propagate heat and the retention of heat within the media, which means, again, how you can manage better your heating process and your energy. And that's what is those graphs on the bottom of the slide here illustrates. Basically, during the trial, we're looking to how long it would take to achieve the optimum temperature, and then how long, once we turn off the heat, how long the ground, the oil would retain that heat, which make then continue to be removable without us continuing to be adding heat. And what we found during the trial is that in 8 hours, we were able to remove 1,000 liters. And if you remember, in 6 years, they removed 6,000 liters. So that really proved that the thermal enhanced process was a viable technology, which then allowed us to move into our full scale implementation, which is in the next slide, please. So based on the findings from the trials and the design stage, we identified the number of locations we had to heat across the plume area, the oil plume area, which is illustrated on the site layout on the top left of the screen. And once we install all the different heating locations, then we move into the phasing of the works, the heating and the extraction. And you can see from the two photos, the oil just coming in a liquid form, very pumpable conditions, and that's because we're just able to achieve those optimum conditions and optimum temperatures, which enables to just remove using normal standard pumping system, and move into the water treatment system, where we could then separate the oil from the water, treat the water, and then recover the oil. And on this job, basically, we remove 130,000 liters over 50 months, reminding that we are removing from the subsurface, so it's a slower process than when compared to removing from lagoons, but was very effective and very successful. And the one key or takeaway from this experience here, and then you transport this to your reality in the Middle East. Point number one is that the recovery of oil can be achieved, of high viscosity oils can be achieved under heated thermal enhanced conditions. In many cases, when you apply in the Middle East, you may be looking to recovering the crude to reintroduce to your export pipeline. For these, normally you may have to add to the process thinners and further separation process so that you can then remove the solid contents from your oil and then the water contents before that can be actually reused or recycled into the process. But a very effective, very successful way of recovering oils. Next slide, please. And moving to our second case study today, that's the Grass Mortar Lagoons works we did. This is a site, again, had a legacy contamination, was part of the coking works, so the coal processing works in the UK. And this area received all the liquid effluents from the process, and they were all placed on different lagoons. As you can see on this aerial photo, you can see the different lagoons there. And over the years, the estimation was that with about 50,000 meter cube of tar sludge impacting soils. And the main objective here was to remediate the site so the site could be integrated to the wider country park surrounding. That was considered as a legacy high risk, exposing the community for the oils, the vapors, and there was a desire was really to mitigate that risk by achieving site-specific risk-based criteria. So our assessment of the solutions there, we look into different options. There was a critical drive into reusing as much as possible the material and minimizing the transportation of waste away from the sites because of the communities nearby. So we identified that bioremediation was the potentially most viable and sustainable and cost-effective way of achieving the objectives from the client in this case. Next slide, please. That just some images from the site just before the remediation. So you can see the wide spread of the lagoons and the coal tar sludge, very thick, very high viscosity, very difficult to recover, to remediate. It's very challenging. Next slide, please. So in order to progress with the full-scale remediation, we went through a design stage, and the design stage had two main objectives, really, or three main objectives. Number one, fully characterize the contamination, the sludge profiling through a series of site investigations, so drilling boreholes. In doing that, we could then assess the volume, the vertical and horizontal distribution of the contamination. The second part of the design stage was confirming whether bioremediation was viable. And for these, there was a combination of field biotrials or biopile trials and laboratory bench scale trials looking to aerobic degradation. And in both cases, we could demonstrate that degradation could be achieved to achieve the site-specific targets, but we also identified that we had to achieve the right blending of the sludge, the tar sludge with site's own material, so it could be aerated effectively. And that was also proved during field trials. Next slide, please. So with the design stage completed, confirmation that bioremediation could achieve the mass reduction needed for the site, we move into the full-scale implementation. Before we could start the works, we had to dewater the lagoons. For these, we had a series of pumping locations where all the contaminated water and the floating oil could be pumped, passed through a water treatment system before discharging to the discharge location. And the system basically comprised oil water separation, then sand filtration and activated carbon treatment for the water. Once dewatered, then we move into the full-scale implementation, which is in the next slide, please. So the remedial process is basically comprised into earthworks, the excavation of the sludge, the blending with the site-owned materials. We could achieve a 1 in 4, so basically 25% mass. That gave us a material that could be processed and aerated through windrowing. So the windrowing, as you can see in the sequence, you use a machine called windrow turner. It's a compost machine, and basically what that does, it creates rows of soils which is mixed, homogenized, aerated, and then in part of that process, you can also add nutrients and moisture if needed. So the windrow turn is really effective when we have large areas, so you can achieve very high aeration rates and very high treatability or treatment rates over time. Once those windrows are formed and the soil is aerated, then we move into the monitoring stage, which is the next slide, please, where we look into in situ and then lab testing. So on site, we test for VOCs, we test for moisture, which is really important for the microbial growth. We look at if there's the right temperature, oxygen, and then CO2 as well. So basically the balance between oxygen consumption, CO2 production is an indication that there is respiration taking place. Once the oxygen is depleted, then it's the point where the bio needs to be aerated again. To validate the observations from sites, we then move into the laboratory testing, where we look into TOCs, hydrocarbons, nutrients, moisture again, and the microbial population to identify if there's a growth in microbial population, which takes me to the next slide, please. And we're really looking to here is to observe if the specific bacteria is growing. So we're looking to what's called the carbonoclastic aerobic mesophilic petroleum hydrocarbon degraded microorganisms. What that means is a bacteria that can eat carbon under aerobic conditions and under a range of 20 to 45 degrees temperatures. And with the right conditions of oxygen and nutrients, then the bacteria is able to degrade the hydrocarbons in the different fractions. Next slide, please. And just moving to wrapping up, the conclusions from the job, at the end, we were able to treat 300,000 meter cube of materials that were all treated and reused on site. As we were bioremediating, we were doing the lens formation, and at the very end of the job, the final landscape was just as you can see on the photo. Upon completion, we then cover with a final capping layer of a clean soil from where we could then place vegetation and grow different vegetations there. What that means is that we could then lead into the growth of the increasing biodiversity. So that's something that's being looked quite a lot in the UK at the moment. On this side, we could increase biodiversity by 10% through growing different flowers and plants and enhancing the growth of life. Next slide, please. And just in wrapping up on the bioremediation, some of the conclusions there. Bioremediation is a very effective technology. It works. It uses natural microorganisms. Often the bacteria is already present. It's very rare where you have to do augmentation. But what we really require is an understanding if the conditions are right, as was mentioned by John earlier as well. You need to check the temperatures, moisture, nutrients, and with all right and balance, the microbes can thrive and degrade the contaminants. Another key point here to consider is, and if you take this message away from application in the Middle East, where bioremediation has been effectively utilized, the key point really is that you have to consider that you require very careful design when you're doing the bioremediation. And you have to look into the right conditions of your site. In the Middle East, where in some areas we have excess water, in the Middle East, you may look into the moisture controls, you may look into salinity, some specific aspects where that would potentially influence the bioremediation, the microbes growth. Other than that, it's a very viable technology for high viscosity, heavy end hydrocarbon. It can be widely applied across the globe. So thank you very much. I think that's my last slide. And I'll be happy to answer questions later on the Q&A session.